Welcome to our lecture on metric spaces. Today, we are going to explore a fascinating and foundational topic known as derived sets. If you have ever wondered how mathematicians rigorously define the idea of points crowding together or accumulating in a space, you are in the right place. We will build this concept from the ground up, starting with simple intuition and moving to formal definitions, so you will understand exactly how and why it works. Before we dive into the rigorous mathematics, let us build our intuition. Imagine a massive outdoor music festival taking place in a huge open field. Some people are standing completely alone near the back, while others are packed tightly near the main stage. If you draw a circle of any size around a person near the stage, you will always trap at least one other person inside that circle because the crowd is so dense. In mathematics, a point that has this crowded property is called a limit point. The derived set is simply the collection of all these crowded points gathered into one new group. It is like the ultimate VIP club for points that always have neighbors. Now that we understand what a limit point is intuitively, let us look at how mathematicians formally define this concept. We operate in a metric space, which is just a mathematical environment where we have a specific, consistent rule for measuring the distance between any 2 points. To test for crowding, we use what is called an open ball. You can think of this as a perfectly round bubble of a certain radius centered at our target point. A point is a limit point if every possible open ball around it contains at least one other point from our set. The derived set is the master list of every single point that the set crowds around. To make our definition rigorous, we first need to define the open ball mathematically. Conceptually, this formula describes the boundary of our test bubble. Let us break down the symbols. The capital X represents the entire mathematical space we are working in, like a blank canvas. The function d of x and y measures the exact distance between our center point x and any other candidate point y. Finally, r is the radius, which dictates exactly how large our spherical bubble is allowed to be. If we increase the radius, the bubble expands to include more points. If we decrease it, the bubble shrinks, forcing us to look only at points that are extremely close to our center. Now that we have our open ball, we can construct the strict mathematical test for a limit point. This formula might look intimidating, but it is just a logical checklist. The slash symbol means we take our bubble and deliberately remove the center point x from it, because a point cannot be its own neighbor. The upside-down U symbol represents an intersection, meaning we are looking for an overlap between our hollowed-out bubble and our original set A. Finally, saying this does not equal the empty set means there must be at least one point of A trapped inside. If this statement holds true no matter how much we shrink the radius, then our point is a limit point. This final equation brings everything together to define the derived set itself. Conceptually, this is the filter that scans the entire space and collects only the crowded points. The symbol A prime is the standard notation for the derived set. The upside-down A symbol translates to for all, meaning the limit point condition must hold no matter how small the radius r becomes. In plain English, this formula says that A prime is the collection of all points x in the space that pass the limit point test. If a point passes, it joins the derived set. If it fails even once for a specific radius, it is rejected. Before we move on, let us see this with a concrete example to build our confidence. We are given a finite set of numbers on the standard real number line. The set A consists of the numbers 2, 5, and 8. Our goal is to find the derived set of this specific collection of isolated points. To do this, we need to check if any point on the number line has points of A crowding infinitely close to it. Let us test the point 2 to see if it is a limit point. We start by choosing a specific radius for our test bubble. We pick a radius of 1 because it is smaller than the distance between 2 and the next closest point, which is 5. Continuing with our test, we calculate the exact boundaries of our open ball. On a standard number line, a bubble around the number 2 with the radius of 1 stretches from 1 to 3. This creates an open interval, meaning it includes all decimal numbers between 1 and 3, but not the edges. Now, we apply the limit point test to our interval. We look inside the bubble from 1 to 3, but we strictly ignore the center point 2 itself. When we do this, we see that neither 5 nor 8 are inside this bubble. We chose a small radius specifically to test if the points are truly crowded right next to our target. Because the overlap with our set A is completely empty, the number 2 fails the test and is not a limit point. Since the exact same logic applies to 5 and 8, none of the points in the set are limit points. Furthermore, no empty space between the numbers can be a limit point either, because we can always draw a small enough bubble that traps nothing. Therefore, the derived set is completely empty. This makes perfect physical sense. A finite number of people standing in an infinite field cannot form an infinitely dense crowd anywhere. The final answer is the empty set. Now let us look at a slightly more complex example where points actually do crowd together. We will examine a set of fractions on the real number line. The set A is defined as 1, 1/2, 1/3, 1/4 and continues infinitely. Our task is to find the derived set for this infinite collection of fractions. To solve this, we need to visualize where these fractions are physically located. We can write the general pattern for every single point as 1 divided by n, where n is a positive whole number. As we plug in larger and larger whole numbers for n, the resulting fraction shrinks. This means the points are packing tightly together in a specific region. To identify the exact location where this infinite crowding occurs, we evaluate what happens to our fractions as n grows infinitely large. We take the mathematical limit as n approaches infinity of 1 divided by n. The symbol representing infinity shows that we never stop increasing the denominator. As the bottom of the fraction explodes in size, the overall value of the fraction gets infinitely close to 0. This proves that the points are accumulating tightly around the 0 mark. Because the points crowd infinitely close to 0, any bubble you draw around 0 will trap infinitely many fractions from our set. Because every possible bubble around 0 traps points from our set, 0 is a limit point. In fact, it is the only place where this crowding happens. Notice a fascinating detail here. 0 is not actually a member of the original set A, because 1 divided by n never exactly equals 0. But it is still the limit point. The derived set is simply the set containing this single point, 0. Physically, this tells us that if you follow the sequence forever, 0 is the ultimate destination or center of gravity for all these points. Let us look at a diagram that perfectly illustrates this crowding effect we just calculated. You are looking at a standard real number line. Notice the blue dots representing our fractions? They start spread out near the number 1, but as you move left towards 0, they pack so tightly together that they form a solid blue line. The prominent red circle highlights that 0 is the ultimate destination of this crowd, making it the sole member of the derived set. This visual confirms a crucial concept. A limit point acts as a center of gravity, and it does not even need to belong to the original set to pull the other points towards it. You might be wondering, why do we care about derived sets? In the real world, derived sets help us understand boundaries, stability, and accumulation. For example, in physics and engineering, when studying a vibrating engine, you want to know if the vibrations will settle down to a specific stable state or spiral out of control. The stable states act exactly like limit points, drawing the system's behavior toward them. By finding the derived set of all possible states, engineers can predict where the system will eventually end up. Similarly, in computer science, clustering algorithms use these concepts to group massive amounts of data, identifying the dense regions where data points naturally accumulate. We have covered a lot of ground today, so let us summarize the most important ideas. First, remember that a limit point is simply a location where a set infinitely crowds together. Second, the derived set is the master collection of all these limit points. It acts as a mathematical filter that strips away isolated points and keeps only the dense locations. Finally, always remember that a limit point does not have to belong to the original set to act as its center of gravity. You have now mastered the foundational concept of derived sets, which is the key to understanding how mathematical spaces behave when things get infinitely close.